SwayamPrabha. Digital India. Educated India.
In this lecture, we are going to look at relative motion. This is a very important concept in kinematics, and this actually complicates kinematics to a large extent. So, it is very important to understand how relative motion is described kinematically. To give you an overview of what we are going to discuss in this lecture is relative motion in non-rotating frames. Before we go to this topic, let me briefly tell you about general curvilinear motion and curvilinear translation, the difference between these two kinds of motion that we can have. Suppose there is a frame which is moving on this, the origin of the frame is moving on this green path. So, it is maybe a part of a rigid body or something. So, it is moving on this path, but it is not changing its orientation, its direction. So, this axis and this axis, so they are parallel. So, it does not change as it moves, as the frame moves, the directions do not change, the unit vector directions which define the frame, that does not change, but it can otherwise move, the origin can move on a curved path. Such a frame is a non-rotating frame, and such a motion is called curvilinear translation. This is a kind of translation, it is curvilinear, but it is translation. Why translation? Because it is not rotating. Whereas, if you have a general curvilinear motion will come with translation as well as rotation. So, this is a general curvilinear motion which has a rotating frame. So, you see the path is curved, of course, and the frame is also rotating. So, it is changing its direction, the unit vectors which define the frame, they are changing directions. So, it is a rotating frame. We have therefore this curvilinear translation and general curvilinear motion. In the curvilinear translation, the frame is non-rotating, whereas general curvilinear motion, the frame can rotate. The path of the point can be arbitrary. We will start with this non-rotating frame. We start with relative motion in non-rotating frames. Imagine that we have this frame xy which is fixed in inertial space. So, this frame is fixed in inertial space, whereas this x prime y prime, this can be a general moving frame, but it is a non-rotating frame, non-rotating moving frame. I can describe a point A in the fixed frame xy, which I have done here on the left hand side, and I can define in terms of what this x prime y prime frame, where the x prime y prime frame is located, which is indicated by this vector RB. So, this is the position vector of the origin of this frame x prime y prime, and R A stroke B is this vector which an observer sitting in frame B sees to point A. So, R A with respect to B is the position vector of A with respect to an observer who is sitting at the origin of this x prime y prime, which is B. So, the observer is B observing this point A, which might be moving, and that vector is r a relative to b. Therefore, we can write r a is equals to r b plus r a relative to b, which is straightforward. I mean, you can see from this figure. Now, if you differentiate with respect to time, then r a is the, when you differentiate r a with respect to time, it will give you the velocity of point A. Similarly, if you differentiate r b, which is the position vector of point B, then you will get velocity of point B, and if you differentiate with respect to time that relative vector r a relative to b, you will get velocity of a relative to b. And here you see there, because the frames are non-rotating, x prime y prime frame is non-rotating, right, x prime y prime frame is non-rotating. So, you have only this relative velocity that you can see. So, sitting on at point B, that means sitting in frame x prime y prime, whatever velocity you see of particle A is this velocity VAB, A relative to B. Velocity of particle A relative to B, that is this velocity. VB is the velocity of the observer B, and VA is the velocity of particle A. Now, velocity of particle A is in the absolute frame, the xy frame. Velocity of particle B is in the xy frame, the absolute frame, but velocity of A relative to B is in the local frame x prime y prime, which the observer B is observing. So, an observer who is sitting at the origin of xy frame will see the velocity of A, measure the velocity of A, which is VA, measure the velocity of B, VB, but this velocity of A relative to B is measured by an observer sitting at B. Now, if you differentiate once again, you will get acceleration of A is equals to acceleration of B plus acceleration of A relative to B. Acceleration of A is the acceleration that is observed by the observer sitting at the origin of xy. Acceleration AB is observed by the observer at xy origin sitting in xy frame and observing point B, which is the origin of x prime y prime. So, that is AB, acceleration of B, as measured by the inertial observer in xy. Whereas acceleration of A relative to B is the acceleration of the particle A as measured by an observer sitting in the frame x prime y prime. The observer is B here. So, whatever is the acceleration as measured by the observer B in x prime y prime, that is A, acceleration A relative to B. Acceleration of A relative to B is the relative acceleration as measured by B sitting in x prime y prime. All these vectors of course must be represented in the same coordinate system for or coordinate frame for this vector relation to be valid. So, either you can choose xy frame or you can choose x prime y prime frame. Okay. So far so good. Now, let us understand this with a problem. Here there are two cars A and B. At the instant shown, car A has a speed of 100 km per hour and acceleration of 8 km per hour per second, while car B, which is on a curved path as you can see, has a speed of 100 km per hour, same as A, and a deceleration of 8 km per hour per second. So, car A is accelerating while car B is decelerating. Determine the acceleration that car B appears to have to an observer in car A. So, this is clearly a problem of finding the relative acceleration of another body, which is B, as measured by an observer sitting in a moving frame, which is A, but moving but non-rotating frame. It is a moving frame but a non-rotating frame. So, here I have the coordinate system which I use. I have fixed up I cap and j cap at the location of B, at the current location of B, but remember this I cap and j cap are fixed coordinate system, they are not moving with B, they are not rotating with B. B is a rotating car, it is rotating because it is moving on a curved path, but xy, the I cap j cap frame that I have shown here is a fixed frame. I am using it to represent things. Okay. Now, that I will use this frame to represent all vectors. So, I will use this I cap j cap frame to represent all vectors. Now, here we are given that velocity of A is 100 km per hour, acceleration of A is given as 8 km per hour per second, it is 2.22 meters per second square. Now, velocity of B is 100 km per hour same, so which when converted to meter per second is 27.78 meter per second, this is same as VA, and acceleration of B is minus 8 km per hour per second, which is minus 2.22 meters per second square. We have to find out the acceleration of car B as seen by car A, and that is represented by this acceleration of B relative to A. So, this is what we are going to find out using the fixed xy frame. Therefore, so the acceleration of car A is 2.22 I cap meter per second because it is accelerating in this direction, that is AA, acceleration of A. Acceleration of B now has acceleration because of two things. One is the tangent acceleration, tangent to the path, this we have discussed in the previous lecture. So, acceleration of B, of car B, is the tangent acceleration, tangential to the path, tangential acceleration, and this is the normal acceleration, normal to the path because of path curvature, and this is what we have discussed in a previous lecture. Now, this tangential acceleration is minus 2.22 I cap because it is decelerating, and the normal acceleration because of its velocity on a curved path. So, Vb square by rho, rho is given as 300 meter and velocity of B is 27.78. So, this square by 300, so that turns out to be 2.57, and it is in the direction towards the pole or center of curvature. If you use the tangent normal coordinates, then it is towards the center of curvature. Okay. Then acceleration of A relative to B, this is the expression we have seen just now. Acceleration of B relative to A is acceleration of B minus acceleration of A. This follows from the relation we just now derived, and if you just plug in these expressions, if you just plug in this and this into here and simplify, this is what you will get, minus 4.44 I cap plus 2.57 j cap meters per second square. So, this is the acceleration vector, relative acceleration vector as seen by an observer sitting in car A observing car B. So, this is the acceleration of car B relative to car A as seen by the observer in frame A or car A. Now, let us come to a very practical problem that we face if we do not have mud guards on our cycles, and many cycles nowadays do not have mud guards. A man bicycles on a muddy street at a velocity v. The bicycle does not have mud guards. Determine the maximum velocity V max such that the mud does not splash on him from the rear wheel. This is a common problem we face if we do not have mud guards, and if you are bicycling on a muddy road, then this mud gets splashed. we have to find out what should be the maximum speed so that it does not splash. Now, to simplify the problem, what I have done is I have asked what should be V max, so that this height, this is the maximum height that is reached by any mud particle starting from anywhere on the rim of the rear wheel. So, I consider that from all points on the rear wheel, mud will be splashed. At some point it will get loosened and it will move in a projectile path. What should be the maximum speed, so that the maximum height that a mud particle can reach at that speed is this h. H is measured from the center of the wheel to this seat. It is very convenient to look at this problem in the frame of the bicycle. Why? Because in this frame, as I have shown you here, xy is the frame which is fixed to the center of the rear wheel. Now, this xy frame is a non-rotating frame, it is a translating frame, it is in pure translation, it is not, there is no rotation. So, it is translating with the bike, it is not rotating with the wheel. Okay. Now, in this frame, the wheel is fixed. Fixed means the wheel is rotating, just rotating in this frame. There is no translation velocity. I do not see the translation velocity of the bike. Therefore, at all points wherever mud is splashed, it is splashed tangent to the wheel. So, wherever mud is splashed in this frame, it is all tangent to the wheel, but in the absolute, for a pedestrian, for example, who sees this person bicycling past, the mud particles will have this additional velocity because of the motion of the bicycle. By putting the frame on the bicycle, we have eliminated that motion. Therefore, it is only because of the rotating wheel, and this you can do by putting the bicycle on stand and on a muddy pool, and if you just drive the pedal, you will find that all the water particles or mud particles, they are getting splashed tangent to the, they are leaving the surface tangent to the wheel. Okay. The mud travels as a projectile starting from all points on the circumference of the wheel. Okay, this is an observation. Now, let us consider a mud particle that leaves from this angle, from a location whose angle is theta. In this frame xy, at an angle theta, there is a mud particle which was sitting here, which is projected along this velocity direction. Now, the position from where the mud particle starts is r cap, is minus r sin theta I cap plus r cos theta j cap, which should be very easy for you to represent. So, this is the position vector of the mud particle when it starts. The velocity vector of the mud particle when it starts, it has some velocity. What is that velocity? That velocity is exactly equal to the velocity of the bicycle. Why? Because you see in this xy frame, the wheel, I have the wheel which is rotating, and this point of the bottommost point of the wheel must have a velocity v, which is the speed of the bicycle, because when the bicycle is rolling, this point, absolute velocity of this point is 0, the contact point is 0, therefore, the bicycle moves forward with velocity v. But when I am on the bicycle, I will see this point moving back with the same velocity as the road. So, sitting in the xy frame, therefore, this point has velocity v, tangent and horizontally backwards. Therefore, all points on the circumference of the wheel will have the same velocity magnitude, and it will be tangent to the circumference. So, the magnitude will be the same v and the direction will be tangent to the wheel. Therefore, this velocity, its magnitude is v, and here I have represented multiplied it with a tangent vector, unit tangent vector. So, V times the unit tangent vector was cos theta I cap plus sin theta j cap, which you can see very easily, and therefore I multiplied with the magnitude, which is the speed of the bike. That is the velocity of launch of the mud particle as it starts from this position. So, launch speed is same as the cycle speed in this xy frame. So, now once it is launched, it follows the projectile motion. In the projectile motion, what happens? X double dot, the horizontal acceleration is 0 and the vertical acceleration is minus g. If you integrate it once and use these conditions, because it is being launched from minus r sin theta at a velocity v cos theta in the I cap direction, v sin theta in j cap direction. So, my velocity in the x direction will be exactly v cos theta, and velocity in the y direction at time t equal to 0, it will be v sin theta, but when I integrate, I generate this integral as minus gt, and this was the initial condition, constant of integration. So, that will be v sin theta. So, you can check that at t equal to 0, this is exactly this velocity, the launch velocity. If you integrate this once again and use these conditions, these initial conditions, then you have this constants of integration set as minus r sin theta here and r cos theta here, and these are integrals generated from these terms. So, this is a straightforward step. So, I have the position of the mud particle at any time t. Now, I want to find out what is the maximum height reached. Let us say this particle which left from this angle theta as shown in this figure, what is the maximum height reached by this particle? To do that, I will find out the time it takes for the vertical velocity to reach 0, that means y dot is 0. At what time y dot is 0? So, y dot is 0 when time is v sin theta by g. Y dot is 0 when time is v sin theta by g, which you can see from here. I will find, so this is the time required to reach the maximum height. I will find out y, which is the vertical motion of the mud particle, at this time, which should be the maximum height for the mud particle starting from theta, and that happens to be this expression. When I substitute this time as v sin theta by g in this expression, so that gives me this y max. This is the maximum height reached by that mud particle starting from the theta location. Now, what I want to find out which theta will actually give me this maximum height. So, I have the maximum height of a mud particle starting from theta. Now, from different theta values, I have different mud particles starting. Which particle will reach the maximum height? So, to do that, I will differentiate y max as a function of theta with respect to theta and put it equal to 0. So, this will give me that theta location from which the mud particle will reach the maximum height from among all mud particles starting from anywhere on the rim on the wheel. And if you do this derivative and put it to 0, you get cos theta star. So, this is the very special theta star from where the particle reaches the maximum height, and it is given by gr by v square. Now, if you substitute this value of theta star in your expression of y max, so this you substitute here, then you get y max. So, this is the absolute maximum of all mud particles that start from the wheel. Now, this y max must be less than h, so that it does not splash on the rider, and this is a conservative estimate of course. So, this should be less than h, and if you simplify you get a quadratic in v square, you have a quadratic in v square which should be less than 0, and if you just solve it you will get v must be less than this expression. It is a complicated expression, but you can calculate for your bike using this. So, you know what is the height of the seat, the saddle from the center of the wheel, that is required, and you will require the radius of the wheel and the acceleration due to gravity, and you can find out what should be the maximum speed of cycling, so that even without mud guards the mud will not splash on you. Next we are going to look at motion of connected particles. So, here I have an example where two blocks A and B are connected by inextensible strings or cords, and these cords, they are inextensible, but they cannot sustain compression. Therefore, if these cords can be kept in tension, then the motion of A and B are related, because the cords are by themselves inextensible, but if you keep them under tension, so they cannot take compression of course. If you start compressing, then motion of A and B can be very different, but if you can keep the cords under tension always, then motion of A and B are related. So, they become connected particles. Therefore, motion of A and B are not independent, and this is what we want to find out, how to relate motion of A and B. What you will observe is that here the complicated parts are these pulleys, and that is what we are going to analyze. So, this is a general schematic of a pulley, and this red string is moving over the pulley, it is wrapping the pulley. So, there is a definite wrap on the pulley. I have considered 2 points on that string, the string is inextensible, remember. I have considered 2 points A and B, which are points fixed to the string. They can have velocities V A and V B as I have shown, and the center of the pulley can have velocity V P. So, the center of the pulley has velocity V P, point A has velocity V A and point B has velocity V B. Realize one thing, that this V A is because the string can unwrap on the pulley, therefore, you can have this velocity perpendicular to the string itself and a component which is along the string. So, velocity of A is composed of a velocity which is unwrapping the string on the right side, it is unwrapping. So, it is perpendicular to the string, such a velocity must be perpendicular to the string, and the other velocity is along the string, which means the string is moving on the pulley. So, V A is composed of these two components. Similarly, V B. I mark these two directions of the strings as dA cap and dB cap, these are directions. So, they are unit vectors, dA cap and dB cap are unit vectors along the string. Now, I start looking at the relative velocity. Now, velocity of point A relative to the pulley is VA, relative to the pulley is VA minus VP, this is the expression we have derived. So, velocity of A relative to P is VA minus VP, velocity of point A minus velocity of pulley center Vp. Similarly, velocity of B relative to the pulley is equals to Vb minus V pulley. So, these are relative velocities of these 2 points. These relative velocities by themselves can be arbitrary, because you remember that this can unwrap. So, you can have these normal components as well, but If you consider the projection of these relative velocities along the string, then there is a definite relation. Why there is a definite relation? Because the string is inextensible. The length AB, this curved length AB is a constant. String is inextensible, therefore this curved length AB is a constant. So this whole length is constant. And how to represent in terms of these velocity vectors? We will say that the relative velocity of A with respect to the pulley in the direction dA plus relative velocity of point B with respect to the pulley in the direction dB, that must sum up to 0. Now, this is very similar to the conservation of, say you have conservation of mass, this continuity equations, very similar to that. Here length is conserved, length is being conserved. Therefore, now how to interpret this? If you sit on the pulley, then what is the velocity of A that you will see? If you sit on the pulley, now these are absolute, remember these Vp, Vb, Va, these are absolute velocities of these points. Va is the absolute velocity of point A, Vp is the absolute velocity of the pulley center, Vb is the absolute velocity of point B. But this relative velocity is what an observer sitting at the center, let us say of the center of the pulley, will see. That is the concept of the relative velocity. That is what we have discussed. So, this relative velocity is the velocity of A as seen by an observer sitting on P. Now, what is VA relative to pulley dot dA? Dot dA unit vector. This quantity is the rate at which this observer is seeing A leaving the pulley in the direction dA. So, this is the relative velocity in the direction dA, and this velocity is solely because the string is either rolling or slipping on the pulley. The string is moving on the pulley. This is not because of unwrapping. This component is not because of unwrapping. Therefore, whatever leaves along A must come back through B, or since I have taken dB also away from the pulley, I mean you should notice that dA and dB are taken both away from the pulley. Therefore, this component is the rate at which the string is leaving the pulley and along A, along direction dA, and this second term is the rate at which the string is leaving the pulley in direction dB, and they must sum up to 0. So, the sign of the relative velocity will be decided by this equation. Because dA and dB are both leaving the pulley, so the velocities along these two directions must sum up to 0. Okay. So, this is the explanation of this projection along dA and dB. Now, if you consider a very special case where the directions are both in the vertical, which I call j cap direction, y direction, unit vector along y direction is j cap. So, I take a very special situation where all the strings are vertical, the pulley is moving vertically, and the points A and B are also therefore moving vertically, there is no unwrapping. Then VA relative to the pulley, velocity of A as seen by an observer sitting on the pulley, so that vector will be this magnitude times j cap will be VA vector, which is VA j cap minus VP j cap, everything is in j cap direction. Similarly, VB relative to the pulley j cap is VB j cap minus VP j cap. So, these are the velocities of points A and B relative to the pulley. Now we use our constraint condition that the length AB, the curved length, the length of the string remains fixed, is unchanging. So, it is inextensible string. So, if it is inextensible, then the component of this relative velocity in the direction of motion of A plus the projection of this velocity, this relative velocity in the direction of motion of B must sum up to 0. If you use this condition and you substitute these expressions here and here, if you substitute these expressions, then what you will have is VA plus VB is 2 times velocity of the pulley. Velocity of this point A on the string plus velocity of point B on the string is equals to 2 times velocity of the pulley. Now, we will look at a problem and we will use this concept of relative velocity for a pulley and see how this problem can be solved. I will also show you an alternative method using plane geometry. In this problem, we are to determine the upward velocity of block A in terms of the downward velocity of block B. So, suppose B is moving downwards, we have to find out what is VA and a given value of y, this y is given. So, in terms of y, we have to find out the velocity relations between VA and VB. We are to neglect the diameters of the pulleys. So, these diameters of these pulleys are to be neglected. Now, notice one thing in this problem, VB, the block B will always remain at the center of this span of the string, always remains at the center. Therefore, the motion of block B will be only in the vertical direction. It cannot move sideways, right. It will always remain at the lowest position because on this span of string, inextensible string. So, lowest position will always be at the center. So, here I have marked out VB and the coordinate system that we use. This is the xy coordinate system, x is horizontal and y is vertically upwards. P1 is this pulley. Note that the velocity of the motion of P1 will be same as motion of block B. Therefore, if block B has a velocity VB, then that will be the same as velocity of P1. I have marked these unit vector directions as we have used D1 and D2 in the direction of the string, and I have considered these 2 points C and D on these 2 spans of the string, and notice that this angle I have marked as theta, which I can find out, I will eventually find out in terms of B and Y. With this coordinate system in place, we will write down our relations. Now, at pulley P1, the relative velocity Vc minus Vb, so it is the velocity of this actually is Vc minus Vp1, but remember Vp1 is same as Vb, therefore, I have used in place of Vp1 as Vb, and that dot product with D1 cap, that means projection along D1 cap, plus Vd, which is this point, Vd minus Vb, again this was Vp1, which I have written as Vb. So, Vd minus Vb dot D2 unit vector, and the sum of these 2 projections must add up to 0, because the string is inextensible. Now I open up the bracket, use distributive property. The first term is simple, Vc dot d1 cap, this should be d1 cap, minus Vb dot d1 cap plus Vd dot d2 cap minus Vb dot d2 cap. Notice here that this point D cannot move in this direction, this point D cannot move in the direction of this fixed end, it can only move perpendicular. This point D can only move perpendicular to the string, it cannot move towards this fixed end, because if it does, the string will become loosened, right, it will collapse. Therefore, this point D can only move perpendicular to the string, it cannot move along the string because it is fixed at one end. Therefore, Vd dot d2 cap must be 0. So, that is our equation 1. So, we have a simplification, Vd dot d2 cap is 0. Now, at pulley P2, here I have the direction j cap, this is towards the pulley, and d1 cap notice is also towards the pulley. J cap is towards the pulley, the unit direction along this string is towards the pulley, and d1 is also towards the pulley, d1 cap. Therefore, and also notice that the velocity of this pulley is 0, velocity of P2 is 0. It is fixed. Therefore, Vc, velocity of C minus Vp2, which is 0, dot d1 cap plus velocity of A, which is also velocity of some point on this string, minus Vp2, which is 0, dot j cap must be 0. Notice why again there is plus, because both the unit vector directions are towards the pulley. So, these two velocities also must add up to 0, velocity projections. Therefore, now I represent these vectors, all the vectors in the xy coordinate system. This Vb I have represented as Vb j cap, Va I have represented as Va j cap, and now I substitute all these things in the main equation. D1 and D2 caps, you can find out in this representation of D1 cap and D2 cap in xy frame. This is straightforward. This is a unit vector along D1. I have used this angle theta. So, it is minus cosine theta I cap plus sine theta j cap, you can check. Similarly, D2 is cosine theta I cap plus sine theta j cap. Now, substitute everything, all these expressions in 1. So, I substitute everything in this equation, this is not there, this is 0. I have expression of Vb, Va, etc., and Vc comes from here. So, Vc dot d1, so Vc dot d1 I substitute this here. Once I do all these things, I get this equation minus Va minus Vb sin theta minus Vb sin theta is equals to 0. So, if you do this simplification, you will get Va in terms of Vb. Now, I have written sin theta in terms of y and b. This much is b and this is y. Therefore, sin theta, so this is theta, so sin theta should be y divided by under root of y square plus b square. So, this is what we have. So, that is the expression of sin theta, and this is our answer. This relates velocity of block B and velocity of block A in terms of y and B. Now, there can be an alternate solution method for this problem. You find out the total length of the string. Total length of the string can be found by this length, which is under root y square plus b square, plus this length, which is also under root y square plus b square, plus this length, which is x. So, total length of the string is this, and this total length of the string is not changing as b moves. So, I can differentiate this expression. So, left hand side becomes 0, right hand side I differentiate. You know that y is changing. So, y will have a derivative, b is a constant, does not have a derivative, and x is changing. So, x has a derivative, and if you just rearrange the whole thing, you can get x dot, which will give you the velocity of A. X dot is the velocity of A, because x is being measured like this from a fixed point. You are measuring x, therefore, x dot must be the velocity of A, it is downward velocity if you are measuring downwards. What this expression tells us is, if Vb is positive, then Va is negative, that means it is going down. This is the summary of what we have discussed. We have discussed relative motion in non-rotating frames, and this is where I will close this lecture.